Thank you so much. I very much appreciate the introduction. And I also really appreciate the great work that Subhashish did in introducing what is going on today. I think one aspect that maybe I would like to add to his points is that today when we design hardware, we're really focusing on designing hardware that always correctly works. And as we go forward, we're starting to discover that as technology miniaturizes, if we loosen these boundaries a little bit, we can get much higher efficiency and much better performance. So here's an example for endurance of the today's non-volatile memories. And you can see pretty big variation depending on what kind of conditions you're actually running in. And these things are going to get worse as we push the boundaries into deeper and deeper nanotechnology. So one of the ways to leverage this is to kind of explore the opportunities at the interface between memory and computing, where we start thinking about designing algorithms that are a little bit more memory centric, that can leverage this high parallelism and maybe some ability to do analog-based compute. And secondly, we need to think about resilient computing and algorithms and strategies that are actually natively robust, that can tolerate well variability and errors that you may get in memory and storage style computing. And one of the exciting things that we find is that when we consider this combination of robust algorithms with in-memory and in-storage computing, we can get unprecedented energy efficiency and performance. And this is one of the reasons why my team has started looking at hyperdimensional computing as a strategy. So the way hyperdimensional computing works is it takes the data that is represented using just standard representation. In this example, I have cats and dog images. It encodes that data into hypervectors. So here I'm showing you cat and dog hypervector that are formulated after all of the training has occurred. So with HD or hyperdimensional computing, what would happen is I would encode image of every single cat into a single hypervector, and I would go along and do the same with all of the other cat images I have. To create a class that represents all of the hypervectors, I would just need to add up the representative hypervectors for each of the cat images. And as you can see, this very simple addition is super easy to implement in hardware. Furthermore, when we actually do the similarity check, we would do exactly the same kind of encoding on an image that was just presented for inference. This would generate a query hypervector. And to find whether this query matches one of the classes, all we're doing is just comparing the similarity between them. And if we're using binary representation, this is super simple. It's just Hamming distance. So whichever one is closest Hamming distance-wise, in this particular example, it would likely be a dog hypervector, would be selected. So all of these operations, turns out, you can implement in memory and in storage. So to summarize, the very high level with HD computing, data is represented with these hypervectors that use up to 10,000 bits. Because we can actually use in-memory and in-storage computing, we can get very energy efficient computation. We can also leverage the strength of HD computing in getting super fast training. As you can see here in this example, the training really just involves adding up a bunch of vectors and maybe doing a little bit of tweaking. The process is super fast, which means that you can actually implement this on very small, even sensor-sized devices. As a result, we can support now real-time learning and even some reasoning capabilities. And the best of all of this is that HD computing is very statistical and very robust to errors. So here you can see we ran inference. This was an isolate data set at varying bit rates. And you can see when we use hyperdimensional computing with binary or integer representations, that essentially they're completely unaffected by even very high bit error rates. When we compare that to the state-of-the-art deep neural network, you see that it dies very, very quickly as you start introducing errors in computing. It basically doesn't scale well. HD in floating point has a similar issue, and this is because error in the exponent will cause huge problems in the computation of similarity check. So as long as you can get away with binary and integer, which you can see from this example is just as accurate as using floating point, we're actually in business. So our team has been looking at applications of HD computing in many different areas. Classification was one of the early ones we looked at, and we found that it works well for all kinds of classification that you might do. Clustering also does a great job. We have done recommendation systems, reinforcement learning, and a number of other applications. And generally what we find is that the accuracy we get is fairly comparable to the state-of-the-art algorithms. The energy efficiency is much, much higher, and performance is also much better. And then robustness-wise, it's off the charts better. And this is partly why we have recently gotten a big DARPA grant that has funded design of future HD computing algorithms and design of new hardware that they're going to be running on. So I have given you an example of classification that's relatively simple, where we can assume that we have only a single object or individual or a single animal in this case. So I had in the previous example cats and dogs. But what happens if I have both cat and a dog in a single image? You know, how do we handle that? And classical algorithms don't normally handle it. More recently, people have actually looked at what's called multi-label classification, where there is more than one label or more than one class per sample. And in this example, this would be more than one label per a given photograph. So what I would like to do next is give you an example of how HD computing can be applied to multi-label classification and how it can be accelerated even in today's technology in 3D flash storage. So prior work on multi-label classification mapped problems from single label into single label classification algorithms by basically taking the power set of the labels. So if I have an image that has both cat and a dog, that means that both of the labels, label 0 representing cat and label 1 representing dog, would be set to 1 if both are present. Now, if I wanted to map this into single label problem, what I would effectively do is look at all of the combinations. So if I don't have either cat or a dog, then the label would be 0. If I have one of them, depending on which one, label would be 1 or 2. If I have both, now label is 1, 1, which is a binary 3. So this works great, except for the fact that now you've exploded the number of labels that you need. And this is one of the big issues when you actually try to do multi-label classification in hyperdimensional computing. So with multi-label applied to hyperdimensional computing, we use binary classification model per label. So this allows us to still detect if each label exists, but we use a little bit more sophisticated encoding directly into the hypervectors. So what happens is if I have a particular label that is 0, we have a specific hypervector that actually allows us to represent that particular label as not applying to that particular class. Second, and we do the same thing for all of the zeros. Now, once we have a 1, we would have a different hypervector, which would basically represent the fact that we now have identified that that particular object exists in that, for example, image. So how does this work during inference? We would go through the process of encoding the data, producing the query. We would then do a similarity check. Because all of this is done in binary, Hamming distance is more than sufficient. So now I would compare query to every single hypervector that I have stored for all of the possible labels. And I would look which one matches best. So in this first case, I found that label equals 0 is more similar. So therefore, the output would be a 0. This basically tells us that that particular query was not found actually under the class of label 1. Then we compare to the second one, and we again find that the output is a 0. And we finally compare to the last one. And here we did find that, in fact, we matched. And this is when we output the 1. So the good news are that HD is super lightweight, but it does increase the size of data, because from simple raw data that might be a single number, even an integer number, I have now gone into hyperdimensional space, which has actually maybe 10,000 bits. On the bright side, because of its ability to do encoding, training, and inference in hardware, we can actually leverage the storage-centric architectures to dramatically accelerate it. And furthermore, we could also loosen some of the requirements of memory and in storage computing being always 100% accurate, because as you saw earlier, HD is very robust to any kind of bit error. So what we did in this work is we looked at how we could accelerate multi-label HD using 3D NAND flash. And this is just classical flash that you can buy off the shelf. The idea that we had is that we would use we would perform HD encoding on every plane of a flash chip. And then the top level FPGA accelerator would run, which would run insider code produced by Jason Kong's team at UCLA. It would actually do the training for us. And this is what the system looks like. You can see the top level controller. This is the lightweight FPGA that actually accelerates right in here the training process, versus every single little flash chip, which inside of it is actually going to be doing the encoding of the data. So encoding is done using random projection strategy, which essentially assumes that every piece of data is going to be encoded using a random number. And to it, we're going to be adding these labels that are going to allow us to separate which one of the objects we're actually recognizing. The actual implementation uses a combination of the registers with a CSA and CLA to finally get the data encoded and stored in a buffer, which then is used to feed the data to the top level FPGA for the classification and training. So here at the top level, to do the classification, we first would store all of the encoded data into the scratchpad. And then for the encoded data that we have loaded, we would actually perform the training. And the training would be done directly in an FPGA. So you can see that the encoded data would be loaded. It would be fed into the FPGA infrastructure, and out of it would come these classes, which are then stored back into the scratchpad to be used for eventual inference. So to evaluate this, we implemented it both using C++ on standard systems, and we also evaluated how it would work using the actual 3D flash. We compared it to multi-label versions of k-nearest neighbor, sequential minimal optimization, C4.5 variant, which is a variant of SVM, and a naive Bayes. And you can see here that we use data sets that have quite a few classes. The number of combinations is not an exponential function of the number of classes here, because the data set itself just did not have some of the combinations present. And the number of features is just representative of the features that we extracted and that were used as a part of the training. So when we did the evaluation in Flash, we implemented and synthesized plain accelerator in 45 nanometer technology using Verilog and Synopsys design compiler. And then we scaled it down to 22 nanometers to get more accurate performance numbers. We simulated a top-level FPGA accelerator using Xilinx tools. And then we compared the proposed implementation with the actual design on and with the run on Intel server, basically. And you can see the SSD parameters that we use. These parameters are pretty comparable to the SSD that you can buy in the market today. So when we look at inference, HD inference performance, energy, and accuracy, we can see that our design of multi-label HD is on average about 5% more accurate than state-of-the-art algorithms. We also see that PowerSet version of HD, so this would be similar to state-of-the-art approach, but implemented instead using hyperdimensional computing, is actually on average about 14% more accurate. So using the PowerSet version gives you more accuracy, but it comes at the cost in size and in speed, because multi-label HD is about twice faster than PowerSet HD when executing. If we look at the 3D flash encoding and training, the differences are pretty striking in both the execution time and in training. We find that multilabel HD is about 47 times faster and more energy efficient than state of the art when run on CPU, but when actually running in flash, we get about 230 more energy efficiency and about 600 times faster execution. So this clearly shows you that when you look at a good combination of changes in an algorithm, data representation, and also the right type of hardware acceleration, you can get pretty dramatic benefits. And this, again, is without considering any bit error rates. So we could get dramatically faster and more energy efficient operation if we loosened bounds on errors a little bit. So to summarize, in future systems, we expect them to use 3D emerging technologies. You've heard this from Subhashish. We find the same thing when it comes to HD computing and its applications. The reason why we're going after this is because we would like to have much better performance and energy efficiency. So we don't want to trade off those two. And this, to accomplish it, we really need novel algorithms and architectures, and we need to be able to design systems that are more robust to errors. HD computing is ideal for this kind of a design because it's super easy to parallelize in hardware and it's very robust. And as you could see from our example, multi-label HD classification ran much faster, about 600 times faster, and was much more energy efficient as compared to state-of-the-art algorithms. Thank you so much, and I'm definitely ready for some questions.